Okay, so class today, as you can see on the board, we got a bunch of different things to do, but two major things. We're going to start out doing a lab, and both of these labs that we're doing today are really more demonstrations where you guys are taking observations. Okay? We don't have enough time left in our density unit in order to do some of these activities fully, and I also don't have enough materials for everyone to do this, but they're going to be some fun demonstrations. We're going to start out with lab 16, and then we're going to take a little break, because it's probably going to take a few minutes. Okay? After we take our little break, we're going to go into lab 18, which is a slightly different topic. You'll find out about that in a bit. And then if we have some time left, I'm going to give you an opportunity to work on your review sheets. So that's your first reminder. Your homework for tonight is that your test review sheets, your density test review sheets, are due tomorrow at class time. Okay? Again, I'm only going to be grading on completion. The whole point of this is not to get everything right. It's to identify what you don't know. So I want you to make an honest attempt to complete everything. And by honest, I mean I want you to work really hard to try to complete everything. Okay? And if you're not able to complete everything, then you should be talking to me or talking to other classmates. And if you still can't find an answer, then it's okay to come in class with something left blank. I'll take really brief questions, and then I need to move on to our first lab. Colin.
What about
Lab
lab 17?
17, believe it or not, was the Cartesian diver. Okay, if you go back in through your lab notes, you should see a lab 17 with that Cartesian diver outline that I already gave. That was, we kind of skipped ahead and we're skipping back now. Okay. Dylan.
When is the test going to be?
Test is going to be next Thursday. It's up on Schoology. Okay, please make sure you use this time. You have a week from today. Use it well. Be studying a little bit every single night. Matthew.
When we're working on our review sheet, can we ask you a question?
You can. Yep. Brenton?
Tomorrow, it's like math camp, we have this competition at Rock.
Yes. So for those of you that are in math counts, what I would say is bring your review sheets into me on Monday. Since the test isn't until Thursday, there's still plenty of time. I will be posting review sheet answers on Schoology over the weekend. Okay, so if you're in math counts, just make sure you show me your review sheet on Monday so I can see that you've done it. And if you have questions about it, we'll talk about it next week. Okay.
Are you going to take our review sheet?
I am not going to take your review sheet. I'm literally going to look it over and make sure that you've written good, decent answers and made an attempt to answer everything. Last question, Fajiro.
Are you ill? Because you never let us have a break.
Am I ill? No, Fajiro, I'm not ill. But it's a great question about why I'm letting you have a break today. And the answer is because since both of these labs are not labs where you guys are interacting as much as you normally do, most labs that we do, you guys are up and moving around and you're doing different measurements. Since both of these are labs where you're really just making observations, I thought it might be nice today to give you a little break so that you can stand up, you can move around, you can get a drink, go to the bathroom, all those things.
Does that mean
But I appreciate you were inquiring about my health. I'm so glad you're concerned. Thank you.
Well, does that mean
Okay.
you want laptops?
We'll discuss that when the time comes. All right, I want you to turn your attention over to the side here. Okay. So I have set up a number of balloons and a number of beakers containing water. And in these beakers, like I said, it's just water. And if you want, I'll let someone go ahead and take a little waft. Remember, we're wafting, not sniffing. Wafting, any odor that you can discern. It's not rubbing alcohol that I'm trying to disguise here, anything like that. No wafting, no, okay, nothing, good, good. Oh, I'm sorry, we need one more?
Yes.
You need two more.
Clear opinion?
On me.
Okay. All of these beakers are filled with water. The only difference between the beakers is that the beakers are filled with a different temperature water. Okay? This water is fairly cold. This water is straight out of the tap, lukewarm water. This water I've been putting on the hot plate, it's fairly warm. Okay? So I've got beakers filled with 3 different temperatures of water, and in front of them are balloons that are filled with the same temperature water as the beaker they're in front of. So this is a balloon filled with cold water, this is a balloon filled with tap water, and this is a balloon filled with warm water. Okay? I also have a final balloon over here which didn't quite freeze, I didn't leave it in the freezer long enough, but it's a balloon filled partially with ice. Okay? The whole point of our demonstration today is to answer one key question. And that's, does temperature have an effect on density? Okay? But before we get to that, let's do a super quick review. Mr. Dillon, can you tell me what density is? Give me a definition.
Density is, density is the,
You got it.
the compactness of the.
Yes, how tightly packed something is. Absolutely right. Let's see. Oh, Caleb. Well, all right, hold on. We're going to save questions for a second. Anaya, what things do we know that can have an effect on density, that can change density of an object? What can we change about an object in order to change its density?
The mass of volume.
We can change the mass or the volume, right? We can add more mass or take mass away from an object. We can potentially stretch that object out or make it more compact in order to change its density. Sure. Okay. Fujiro, how do we calculate density? Mass divided by volume. Well done. All right, one more. Who can tell me Xavier can tell me, because he's got his hand up there. Xavier, what's the common unit of density that we've been using in class for the most part? G over ml, and G stands for? And ml stands for? Milliliters. Grams divided by milliliters. That's right, okay. Is that the only unit of density that exists out there? No. Really, we can make, as long as we're taking any unit of mass and dividing it by a unit of volume, we have a unit of density, right? We could have density in kilograms per liters, all right? It doesn't have to always be grams per milliliters. What's that?
Are you going to test us on that?
I will not test you on that. Okay, don't worry. Okay, all right. If these are these really urgent questions? Because I want to get to this before the temperatures change too much.
It's a question about the lab.
Okay, question about the lab. Go ahead.
Are the balloons filled with the same amount of water?
The balloons are filled with approximately the same amount of water. I tried to get it right by using a syringe. Okay, I may have been off just slightly here or there, but I think they're pretty darn exact. Yes?
Well, for the review sheet, will we have time to check it or no, in class?
Let's not talk about the review sheet right now because I want to get to the lab. Okay? If these are questions specifically about the lab, let's take them now. Grace?
Will it matter if the balloons have different weights?
We're going to find that out. Okay, let's save that. All right, so this is how you guys are going to record as observations as we go. Okay, the purpose of the lab, again, is to test to see whether density is affected at all by changes in temperature. Okay? What we're going to do here is I'm going to start out using the hot water balloon. So if you're looking on your lab sheet, we're going to start out by filling all of the boxes in that are in the second column. Okay? I'm going to place that hot water balloon in hot water, and then in tap water, and then in cold water. And all you're going to write down is you're going to write down whether that balloon floats or sinks. Okay? And I want you to write that information small in case there's a few other little tidbits that we're going to put down. Okay? So when I put the hot water balloon in the hot water, you're going to fill in float or sink in that first, the first box in the second column. Okay? And then when we put that hot water balloon in tap water, you'll be filling in the second box down in the second column. So we're just essentially going to go down or up the columns, and then we're going to go across. Okay? We'll do hot water balloons first, and then the tap water balloon, then the cold water balloon, and then the ice balloon. Okay? Dylan, is it really important?
Yeah, too quick.
Okay, it's got to be real quick, buddy.
If you put those balloons like the hot water balloon in the cold water, won't it affect the temperature in the balloon?
True, which is why I'm going to try to do them in order of hot water balloon in hot water first, and then in tap water, and then cold water. And we're not going to let them sit in there for too long. Okay? All right, Brenton and Xavier, are we ready? Good. All right, so we're going to start with the hot water balloon first. Okay? Before I put this in, I want to hear a prediction. What do we think is going to happen when I take the balloon filled with hot water and put it in roughly the same temperature water? Cameron?
I think it's going to be just a little bit less dense because I think balloons, like the fabric of the balloon is less dense than water.
So the fabric itself may be less dense than water?
Yeah.
Okay. Good idea. Yeah, Grace?
I think it's gonna
Okay, all right.
I think that it's gotta like stay at water level, because it's like kind of the same temperature. Like
So you think it might do what we call subsurface floating?
Yeah.
So it'll actually go down and it won't be on the surface, but it also won't be on the bottom. It'll be right in the middle of the water column. All right, we got 3 very different answers. Let's see what happens. All right, now it floats, but I would record that it's barely floating. There's an area about the size of a dime of the balloon that's actually above the surface. Everything else is under the water. So it definitely floats. It's not quite subsurface floating. For that to happen, it really has to be all underneath the water. Okay? But it barely is up there. All right. Now we're going to go down that column again. So we're going into the next box below. We're taking that hot water balloon and we're putting it in tap water. I want to hear from someone different this time. Predictions. Matthew.
Well, I don't know if this is true, if it's like true with milk, but like when you heat milk up, it gets thicker.
It's thicker. Interesting.
So I think that
So
adds.
you think the hot water might be more word, more dense?
Yeah.
Possibly. Okay.
Today,
Kajiro?
I think it's gonna sink.
You think it's going to sink? So along the same lines as Matthew, if it's more dense, it's going to sink, right? You think it's going to subsurface float? Well, let's find out. Brenton, I'll get you on the next one. Okay, that's fine. Just make sure you bring, Anaya, just make sure you bring your data sheet with you. Kajiro, you're really good there, buddy. Fine. Okay, here we go. Hot water balloon in the tap water.
Wow.
It floats, and it floats higher than it did in the hot water.
Wait,
Okay? Significantly higher than it did in the hot water. Okay, Dylan.
when it was in hot water, was like how tall?
I said it was about a dime-sized portion of the balloon that was above the water level. This time, I would say it's much more than a quarter-sized portion of the balloon.
Like a dollar
Okay.
coin.
Like maybe $1 coin. That's right, yeah. Sarah.
So we write barely float?
I think you would write float on this one.
Okay.
And you might also want to write that it floated higher in the water than it did in the hot water.
I'm not writing it small enough.
That looks great to me. Well done. All right, last one, and I'm going to let Brenton do this one to start out. Brenton, what's going to happen when we take this hot water balloon and put it in the cold water?
It's gonna float a lot.
Okay, you think it's going to float more than it did in these other ones, or float higher in the water than it did in the other two? Possible. Caroline?
I think it's gonna be the same thing as Brenton.
Same thing as Brenton. Okay. Xavier?
I agree with Brenton.
All right, we got a lot of people agreeing with Brenton. This is great. Tahari, are you going to disagree?
I think that it could go either way.
Okay.
I mean,
That's
because
fine.
it was barely
Sure.
floating with the hot water.
Let me call you, but you've already called on quite a bit. So I'm going to give other people a chance for now, okay?
Because it was barely floating in the hot water, and when it was like floating a lot in the tap water, so it was
Well, let's find out before this thing gets too cool. It definitely floats, and I would say it floats
The same.
even, well, it's close. I would say it's about the same or maybe even a little bit more than it was in the tap water. Yep, probably slightly more than it did in the tap water. Okay, Mr. Koff, do you have a question, sir?
Well, it's about my revolver.
Your data sheet?
Yeah. Is it okay
Yes.
if I number the boxes so like I could see like floating greater than 1?
Sure.
Nice question.
No, because we're gonna do that. We have a fourth balloon. We have a balloon filled with ice. Dylan.
I have a question about the thing. Is it like, I forget what it was like. Does it like, if you were to like drop, like what, you know how we had those like things in the oil?
Yes.
Yeah. Is it like, if you were to have like, on hot water and cold water, are they not like, do they not want to like mix together so then it just more force, there's more cold water pushing it up?
Well, remember that we have these things surrounded by a balloon, right? So they're definitely not going to mix together. But think about this: if you were to take hot water and put it in a bathtub, and then all of a sudden realize it was too hot and start adding cold water, do you notice like a distinct layer of cold water
Yeah.
versus hot water? You do?
Well,
you can't see it, but it feels good.
Well, you can feel it, right? You can feel the layer, but you can't necessarily see it. And we're going to talk about why that is in just a little bit. Okay, hold on. We got to move. Got to move before that ice balloon totally melts. Okay, all right. So tap water balloon. I'm going to go a little faster this time. We're going to start out putting the tap water balloon in the tap water. So we're going to write this one in the middle box of the third column. Okay, middle box of the third column. Tap in tap. We're going to start here. I'm hearing sink. Anyone think it's going to float? Float maybe. Subsurface float possibly. Let's see what happens. See if I push it down, maybe it'll. Nope, still coming up. It floats, and interestingly, it floats to about the same extent that the hot water balloon did in the hot water. I would say there's about a dime-sized portion that is showing. Okay? So if you want to call it barely floating, you can call it that.
Maybe it has something to do with the...
Maybe. Maybe. Let's wait on that, though. We're going to get to conclusions in a second. All right. Tap water balloon in the cold water. I'm going to save predictions for right now. We're just going to put this in here so we can go.
Is that the cold water?
This is in the cold water. So you're doing the bottom box right now.
Barely floats.
And it floats.
Barely.
And interestingly, about the same as it did when it was in the tap water. So it barely floats, but it's up there.
It's like a
Okay. Anyone have any predictions about what's going to happen in the hot water? Mr. Kalev, I haven't heard from you today. It's going to sink. Interesting theory.
No, I think it's gonna be like in the middle.
Let's test it out. Let's see.
Guys, come on, it's gonna sink.
Yep, it's in the middle.
It's in the middle.
It's in the middle.
Hold on.
It's bouncing.
It's bouncing.
And don't sink.
And it's settled. It's on the bottom. It sunk. Kalev, well done, sir.
I knew that.
Congratulations to you too. Okay.
It's our first sink of the day.
It is our first sink of the day. It's exciting, isn't it?
Oh,
It's exciting. All right. All right, now, what we're going to do, we're going to go a little faster, but what I want you guys to start looking at here is, are we developing a pattern?
Yes.
Right? I can tell you we are. We're developing a pattern. So as I go through each one of these, I'm not going to call out for predictions quite as often here, because I still want to get to that ice balloon before it totally melts. But what I do want you to do is silently make some predictions in your head. Think about, all right, when he puts this cold water balloon in the cold water, what should we see? What should we see in the tap water? What should we see in the hot water? Look back at your other things that you've written down, your other observations, to help guide those predictions that you're making. Okay? All right, cold water balloon in the cold water. Put it in there. It barely floats. This is probably the lowest floating one that we've had. It is, I would say, much less than a dime-sized portion is above the water level. So it's very close to subsurface floating, but not quite. Okay.
I think the colder the balloon is.
Dylan, let's wait on conclusions just for a little bit. I know. I promise you'll get the first crack at a conclusion. Okay.
It's cold with cold.
Cold with cold. So barely floated. All right.
Is the hot one like running in?
Don't you see the scars? No, it's not that hot. All right, cold water balloon in the tap water.
Oh, cold.
Sigma.
Hold on.
Subsurface.
Oh, shoot, I wasn't supposed to do that. All right, so just so you know, it is whoa, actually, hold on.
Get the.
Yeah, it is once again barely floating. It is so barely floating, that's definitely the lowest we've had. It's almost subsurface. Now, if everything, I'm going to tell you this, if everything had worked perfectly, this would have sunk.
Should we say
Okay.
sink?
No, I want you to record what we saw, so that it did float, but it was by far the lowest floating of any of the balloons that we've had so far. And notice how when I push it down, it takes quite a while for it to come back up, especially if I don't let it bounce too much. It takes a while to come back up before it does.
It could have been something.
Now, I think if I had this sitting in the cold water for a long time and kept the water inside here fairly cold, we would have seen it float. I mean sink, I'm sorry, we would have seen it sink. but it probably, the water in here warmed up a little bit as it was sitting on the counter. Okay? All right. Cold water balloon in the hot water.
Subsurface.
It is definitely a sink. It bounced a little while, but it is down there. It sunk. All right, now, we have seen what should happen, and there is just a barely little bit of ice in here, so hopefully things will happen as they're supposed to. I don't know. Most of the ice is melted. We may get some strange results. But based on what we've seen so far, who can tell me what should happen with the ice? Fajiro, what should happen?
Sinks. My conclusion is the colder it is, the more it sinks.
Okay, so Fajiro's saying the colder it is, the more easily it sinks. Grace is adding that the colder it is, maybe the more dense it is. Ice, we certainly would assume, is colder than regular water, than liquid water. So we should see it sink in all of them. Let's see what happens. What the heck is going on?
Oh, ice
It's
does float
floating.
in water.
Wait a minute. Cameron, tell me what we got going on here. Seriously?
Because you know,
It floats.
like when you freeze ice, like it gets like bigger, kind of.
Interesting.
Getting cold.
Okay.
So it's less.
Now, let's just try it in the other two to make sure we can verify our results. That was in cold. Yeah. So write down that the ice balloon in cold floated. And it wasn't even a barely float. That did a pretty good job of floating. Okay.
I know what that.
All right, Dylan, sit down. Save it. I know, buddy, you're excited. We'll get there. All right, ice balloon in tap water. Still floats. Shockingly floats. And ice balloon in hot water. No, it shouldn't do that again. If I truly had enough ice left in here, it should float. But because most of the ice has melted, unfortunately it sank. Okay? So you can write sink, but put a little star by it, and just make a notation saying if there was actually a lot of ice left in there, it would float. Okay?
Supposed to float.
Supposed to float if there was lots of ice in there.
It's supposed to float.
Supposed to float, but I want you to write that it sank. But then also make a little notation with a star saying supposed to float. Okay. Hold on, Dylan. And Matthew, both of you, contain yourselves. Okay, Dylan. I will get to you, I promise. I promise. Okay, let's ignore the ice for a second. And just think about the other ones that we saw. Mr. Dylan, do you think you can try to sum up what we've learned about the effect of temperature on density in one sentence, based on everything else that you saw? I want you to try. Try to put it in one sentence.
Wait, one sentence what I think or what?
What's a general conclusion that we can draw about how temperature affects density, at least for liquids? Because we've really only tested liquids, right? We had an ice balloon in there, but the ice had all melted. Most of the ice had melted. So just for the liquids that we've observed, how does temperature affect density, Dylan? Okay, bring the word density into it. The colder it is.
The colder the water is, the less dense it becomes. The main water, if it's cold,
If
then
it's sinking down more easily, is it less dense or more dense?
the main water is dense. But
Does anyone disagree with that
No,
statement?
but then the balloon is more dense.
Hold on.
Water in the balloon is more dense.
When things sink really easily in water, are they more dense than water or less dense than water, guys? More dense. They're more tightly packed.
I'm saying the main water is less dense. The cold water, and like the main thing is less.
Okay, but so Dylan, what we've seen though is that the colder the balloons were, the more easily they sank in the other liquids, right? So if we can say that, then we should be able to say that the colder a liquid is, the more dense it is, right? There's our conclusion, our first one. I want you to write that down in the notes and conclusions section in the bottom of your page. Fajiro, wait for a second. I want you to write that down. The colder a liquid becomes, the more dense it becomes. The colder a liquid becomes, the more dense it becomes. And end that with, and vice versa, which just means the opposite is true.
Wait, the colder the liquid becomes.
The colder a liquid becomes, the more dense it becomes. I will write it all up here on the board so that everyone can copy it down.
Wait, I don't.
Matthew, just wait a second, please. Not just yet. The colder a liquid gets, the more dense it becomes. And vice versa. And vice versa just means the opposite. So what we're saying by vice versa is we're saying the hotter a liquid gets, the less dense it becomes, right? So clearly there is an effect of temperature on density. If there was no effect of temperature on density, then we would not see any change with the behavior of any of the balloons in any of the different liquids, right? They should all do the same thing, but they didn't. So clearly density is affected by changes in temperature, and that's the effect. Okay? Alright, now, hold on one second, guys. Matthew, I made you a promise that I would get to you, and I will. You just have to show me a little bit of patience. Okay? There's a couple things I want to get through first before I take general questions. Jeremiah, I will get to you too. You just got to show me a little patience. Okay? I'll remember. Trust me. Alright, so the couple that we had that barely floated, like when we had the ice, or not the ice balloon, sorry, the cold water balloon in the cold water, and it just barely floated. Cameron said it might be because of the fact that the balloon itself is made of a material that's less dense than water. I think that has an effect. What else might have played a role in why that just barely floated up? Is there anything else in there that may have been less dense than water?
Well, they're the same densities as the two liquids with cold water.
Okay. The liquids inside should be about the same density because I filled the balloons with liquid from the containers, right? But if any of you have ever tied a balloon, is it easy to get the balloon completely and totally 100% filled with water?
No.
What do we always get a little bit of caught in there?
Air.
Air.
Does it look like a suction
Is
cup?
air less dense than water?
Yes.
Is it possible that I may have trapped a little bubble of air inside that balloon?
Yeah.
And that may have contributed to the balloon being slightly less dense than I wanted it to be? Okay. Is it possible that if we could take out that bubble of air and make it just that perfectly temperature water, the same as inside those containers, that the balloon might subsurface float truly? Okay, it's possible. And maybe I'll see if I can make that happen. It's going to be really hard, but I'll see what I can do. I might have to fiddle with things a little bit. Okay, so I want to take some general questions now, and then we're going to move on. So I'm going to start with Dylan, go to Matthew, and then Fajiro. Dylan.
Is it like when you get some colder water? It's like when you go into like a cold, really cold water.
Hold on one second, Dylan. All right, so there are some people that are being a little disrespectful. Let's make sure we're listening to Dylan's comments. You guys have been great. We're going to take 5 more minutes, and then we're going to take our break. So I'm just asking for 5 more minutes of patience and attention. Okay? We're getting there. We're close. Dylan.
Is it because like when you enter like cold, like if you were to enter a lake that's really cold, and it's like your body sort of like tenses up, and then your blood doesn't flow easily, and it comes more compact. There's less like fluid in it. So is that like it? And then when it's warmer, it's more like moving everything. So it flows.
There's a lot more that's involved with that, and it has to do with certain aspects of human biology that I'm not going to go into right now.
But is that what the balloon?
Hold on. Just because it's a much longer explanation. Okay. You asking the fact that your body feels more tense?
No, it's like when you drop food into the water. So like I don't know, like when you drop.
All right. Let me go through kind of the rest of what I want to talk about, and I may answer your question. And if I don't, when we're during our break time, come ask me again. Okay, Matthew.
Okay, so when we're talking about our conclusion, we're not including the ice, right?
We are not including the ice yet.
Okay.
I'm going to have you write down something about the ice in just a second.
And like, as colder, is that the tap water kind of colder too?
Well, is the tap water colder than the hot water?
Yeah.
Yeah. So all we're saying is, as we go from really hot water to tap water, we should see an increase in the density of that water. And as we go from tap water to much colder water, we should see a continual increase of density, further increase. Okay? All right, Fajiro, last question, and then we're moving on.
Well, I'm asking, it's not going to go green.
Thank you for asking. I appreciate you for asking. Instead of just taking, the answer is no. Okay?
Then how does it go?
I will explain all about that later, but for right now, no. Okay? Alright, so a couple other questions I want us to answer. So we know now that temperature has an effect on density. We know that the colder a liquid gets, the more dense it becomes. I want someone to try to help me with that one big question that we're always asking, which is, why? Why do liquids get more dense the colder they become? What's actually going on inside that liquid? And if you think about what density really is, I think we can get this. And I'm going to give you a little hint, and then I'm going to let Brenton go first because Brenton had his hand up before you, Cameron. Okay? But I'm going to give you a little hint. Remember we said that density is mass divided by volume, which means if we're changing density, we have to be changing one of those things. So ask yourself this. Are we adding anything to the water, or are we taking anything away that would cause a change in the mass? Yes or no?
Yes.
We are changing the mass? What are we adding to the water that's changing the mass?
Climate.
When I make the water colder or I make it warmer, am I adding or taking anything away that's changing its mass?
Taking away
You can take
temperature.
Am I... Tajiro, please don't just call out, okay?
Don't you take this on? Like, doesn't it like take away fluid?
Am I taking away anything physical from the water? Am I removing parts of the water?
No.
Am I adding stuff to the water?
Yeah.
What? What am I adding to the water? Am I adding salt? Am I adding sugar? Am I adding rocks?
No.
Okay. So ask yourself, should the mass change?
No. It's a volume.
No. So if the mass isn't changing, it must be the volume. Now, Brenton, take us home. Why is this happening?
Well, in my old school, we were learning about molecules and
Okay.
like gases, like all the like all flying around, and water is kind of more like
Okay. All right.
and gas is like evaporated water, so like maybe like the hotter the water is, the more separate the molecules are.
There we go. We got to it, okay? All right. So all of these substances that we're working with, water, wood, any liquid, any solid, any gas, all of these things that we see around us are made up of these teeny tiny little particles, right? Atoms and molecules. And when we heat those atoms or molecules up, when we heat those substances up, or we cool them down, we're going to change how closely packed together they are, or how spread out they are. So what's happening when we're cooling down some of this water is that all of those little particles inside the water are getting a little closer together. They're all hovering a little closer together, okay? And since they're hovering more closely together, have we made them more tightly packed? Yes, so we've made them more dense. If I heat them up, then all of a sudden they start spreading out a little bit. They become less tightly packed and they become less dense. I'm not changing the mass of the water. I still have the same water. Dylan, please don't call out. I'm not changing the mass of the water, but I am changing the volume. One thing we know is that when water heats up, even in the oceans, right? That massive amount of water, oceans will actually slightly expand, okay, when they get warm versus when they're colder. That water will take up slightly more space, increase in volume. Okay, all right. We're not gonna talk about why ice does what it does right now, but I am just gonna say this. Water is one of the very few substances that we know of. There are others, but not many, where where the solid form actually occupies more space, has a greater volume than its liquid form, where the solid form is less dense than its liquid form. Think of most other substances you know. If you were to take something like a ball of iron and melt it down, so you have like a big, bucket full of melted iron, and then you take another ball of iron and drop it in. Would you expect that ball of iron to float on top? No, it would sink right down to the bottom, right? But there are some substances, including water, where its solid form will float in its liquid form. And I intentionally tried to deceive you today, but if you think about situations in everyday life where you've observed ice, if you ever add ice to a drink that is mostly made up of water, what does the ice do? It floats on the surface, it doesn't sink to the bottom. So we know that ice is actually less dense. The solid form of water is less dense than the liquid form. Okay, we are done for right now. If you have further questions for me, you can stay and ask me. You have a grand total of 5 minutes. Now here are the rules though. Here are the rules. You are not allowed to play video games during that time. Okay? You are not allowed to go onto your computer in any way during that time. You may go to the bathroom, you may get a drink. If you're going to go out into the hallways, you have to be quiet. Now you don't have to be silent, you have to be quiet because there are other classes going on around. Okay? You can stay in here if you want, but if you want to stay in here, you also have to keep the volume down to a certain level. And I will be here if you want to ask me questions. Alright, you have 5 minutes starting now.
Mohlman, that was my question.
I said what Brenton just said.